So let's understand this inertial circle a little bit more. The point I didn't make it here is that if you had a pendulum hanging here, okay, then in this rotating framework it will not hang straight down. It will point towards this effective gravity. Okay, because it's in a rotating framework. Let's say you had a structure, triangular structure on top, and then you hung a pendulum in the middle. Then, because of this rotational effect, gravity, if this was not rotating, gravity would keep the pendulum straight down. But once you start rotating, the pendulum is going to swing to match this effective gravity or measured gravity that we have mentioned several times already. This is best seen with this example of the Foucault pendulum. When he discovered this in the Parthenon, he argued that this is because of Earth's rotation. Obviously, this doesn't happen in the grandfather clock because it's too small. But if you create a long enough pendulum so that it can feel Earth's rotation, then the pendulum will not just swing back and forth. It'll do this kind of motion that we showed with just a figure on the reference parabola in the previous podcast, right? So this should make it clear to you that this is just a pendulum feeling Earth's rotation. So these inertial circles are real, okay? It's not just a theoretical idea. So we will see soon that this actually also happens in the real ocean. So going further into this rotational framework, writing Coriolis 2 omega u rotation as 0, 0, 2 omega crossed with u rotation, v rotation, and 0. We are still assuming there is no w. Then you can do these cross product. I'm sure you know how to do it with the matrix and so on. You will get minus 2 omega v rotational in the x direction, 2 omega u rotational in the y direction, and 0 in the z direction. This becomes critical to understand when we go to the sphere. Coriolis is acting in the x and y direction, but not in the z direction. Okay, that's simply derived here. So the inertial circles basically come out of the situation where the only forcing is Coriolis. How do we create it? We will see in a minute. So you can go through these calculations by substituting u rotation as dx dt, dy dt, and derive the radius of the circle that will be created by a parcel that is having just Coriolis effect. Okay, so imagine you are in the northern hemisphere, counterclockwise rotation, and you push something and leave it. There is no other force, no friction, and it just feels Coriolis. Okay, so if it's going this way, it'll feel rightward push, rightward push, rightward push, rightward push, and it'll keep on feeling the rightward push and end up going in a circle. Okay, because Coriolis acts continuously. So this is how you would derive the radius of that circle. Obviously I'm not going through the details, but the equations are right there. It's fairly straightforward. So you can see that the theoretical trajectory of the puck that we had seen on our reference parabola that the guy was looking at, if you are on the rotating framework, you would see it. Standing outside, he would just see a back and forth motion. Okay, so that's critical to remember. So the inertial period here is defined by pi over omega, because 2 and 2 cancelled out. You have to figure out how much time it takes to cover 2 pi, right? 360. But it's just pi over omega, and these periods can be pretty long. Writing our equation again in the inertial framework, you remember this form. We derived du rotational dt plus 2 omega u rotational plus omega cross r. We had basically trying to create a situation where all the other terms disappear and the only force left is the Coriolis, and in this case du inertial dt is just omega cross r. So these are balancing each other, and the inertial velocity is just given by the centrifugal force. Again, don't worry too much about it. So this looks very familiar to our original equation, d squared r dt squared equals minus omega squared r. It's just the acceleration in the radial direction related to the Coriolis effect. Long story short, let me just jump through this and go to observations of inertial circles. And their period is given by pi over omega sine phi. We jump a step here because when we go on the sphere, there is a rotation of Earth around its axis, but other than the equatorial circle, as soon as you go away from the equator, you have to consider the local component of omega, which turns out to be omega sine phi. We'll derive this soon in the same chapter in a podcast a little bit later on. But just want to show the inertial circle. This is actual observed currents in a current meter in the main thermocline. We haven't defined it yet. We will later on. Basically, temperature is warm near the surface. There is a sharp gradient, and there is nearly constant cold temperature to the deep ocean. You can again find my podcast on thermocline and look it up. But essentially, if you go below the surface, when there is a burst of wind and then the wind dies away, and you are away from the surface, frictional effects are small. So parcels of water get pushed, and then they are just left alone, and Coriolis is the only force acting. So you can see that these are the 5 inertial periods shown here. An inertial period is calculated using this formula for that latitude of 28 north. Only the latitude matters. Longitude doesn't matter for Coriolis. And the inertial period here turns out to be 25.6 hour. So it's longer than a day. Okay? Earth rotates. If you push and leave things, they can have a inertial circle. Very hard in the atmosphere because friction is much larger and things move fast. I should be careful how I say it, but nonetheless, in the ocean, which moves slowly, you can easily see actual inertial circles. Just go through this so that you are aware of the impacts of rotation and consequences of rotation in a rotating system. We are jumping a little bit ahead and back, showing the inertial circles with local Coriolis before we have put things on the sphere. But that's what we will do next.